Next speaker will be Craig O'Neill from Macquarie University. We're just going to have to do a switcheroo with computer systems here, so just bear with us for about 2 minutes.
All right, so my interest in this anyway, so I'm at Macquarie University up in Sydney, and my interest in this is from planetary science point of view, really. So I get to spend part of my time each day, when I've been in department meetings all day and I come out, you've just had enough, and I can sit down at my desk and watch what happens when I smash asteroids into planets, which is really satisfying. But it's not just fun and games, it has a serious side too, and in fact, asteroid impacts, like the Murchison-style asteroid, but scaled up in size, have had a fundamental effect on the habitability of our planet in terms of its long-term evolution. We've heard a little bit about how Murchison brought in some essential ingredients to life, a lot of the carbon compounds, the components of DNA, amino acids. What I want to talk about today is what asteroid impacts actually do to a planet as it's growing and how they affect the outcome, how a planet ends up after a few billion years of evolution. So when we think of asteroid impacts, so it might be a little different in this town, but generally people think of something like the KT impact, the Cretaceous Tertiary mass extinction that killed the dinosaurs. And we tend to think of it as a very destructive event. We wiped out an entire ecosystem. Huge percentage of Earth's life died during that event. And there's a little graphical representation. It has T-Rex heroically trying to catch the asteroid in its mouth as it's coming down. And so, of course, this fundamentally changed the Earth. I mean, it paved the way for mammals, which was nice. And now we kind of think of dinosaurs taking one for the team here to let the mammals rise up afterwards. But the long and the short of it is, when we think of asteroids, we don't think of anything good happening out of it. But the question I want to ask today is, what do really, really big meteorite impacts do to a planet? And there are a couple of really good examples of what they can do in terms of our long-term evolution, and one we generally see every night. And that's, of course, the Earth-Moon system seems to have formed as a result of a giant impact, and that's had a fundamental effect on the way Earth has evolved through time. And so a lot of this comes out of the post-Apollo mission, so the ideas were evolving. At the same time Murchison was collected, and after the samples came back from the moon, we realized a few things going on with the Earth-Moon system were quite peculiar. The moon seemed to be very dry. It was made up of nearly 80% of the surface is one type of mineral, a type of feldspar, and people were trying to puzzle out exactly how this fit into the scheme of things. And then it got worse and worse. The more that we went on through time and started measuring the Earth, and as we've heard today about isotopes already, the isotopes, kind of like, I like to think of as DNA for planetary scientists or geologists. The DNA evidence on the Earth and the Moon, the isotope systems, are unbelievably similar. So similar that we can't measure the differences between a lot of these systems. The Moon seems like we took a chunk of the Earth's mantle, and put it up into space. And they realized, there's very few ways you can explain this. And the best one at the moment is that the Moon formed as a result of a giant impact. So a body the size of Mars, which we call Theia, mother of the Moon, Greek mythology, came in and hit the Earth in a glancing blow. Something like this. So this is a simulation from Robin Cann up at Southwest Research Institute in the States. And this is what we call the canonical model of moon formation now. We have something the size of Mars hitting a glancing blow, blasting off this disk that rotates around the planet. The entire surface of the Earth is molten a huge amount is vaporized. What's left is molten during that event. So we're talking about a magma ocean covering the entire Earth, probably 600 or 700 kilometers thick. So an enormously violent event. Somehow the rock vapor eventually coalesced in this disk and eventually formed the Moon out of that. And we have, these days, it's very hard to know what the Earth looked like during this because nothing is preserved from this event on the Earth. And I just showed this purely, we have sound. It's a surprise to everyone. Let's see if that, no, I have no control over sound. So this is an example of a lava lake. It's maybe in something like the Earth's surface at that time. This is Urte in Ethiopia, one of the most largest and permanent lava lakes that we have. And I'll see if I can work this way. My cursor gone. Is it a bit? There we are. Excellent. Right. So I'm going to try and zoom forward a little bit, because otherwise I'm going to run completely out of time and Graham's going to get me off stage. But there's some amazing things. What you can see in the middle there, all that bubbling coming up, this is gas. So gas in the lava lakes actually forming these bubbles, and it's coming up and erupting out. But the lava lake's erupting and an enormous amount of gas out of it. So the magma supply that's feeding this thing from depth carries with it a lot of gas and whatnot that bubbles out of the lava lake and actually forms the atmosphere. And in fact, this is probably where a huge fraction of Earth's atmosphere originally came from, bubbling out of a magma ocean or volcanic systems through time. And if we go a little bit forward in this again, I'll see if I can get it right. This is a time lapse, so they're taking a shot every 30 seconds, and you can see these huge rafts of lava just kind of moving over the lake. You got little bits where they're splitting apart and it's hot, and then the lava cools down and forms this crust on top. And from a dynamics point of view, this looks an awful lot like the surface of the Earth right now. We've got these kind of pseudo-tectonic plates floating around on top of this convecting magma system. But this is about as good an analogue as we've got of what the Earth was doing for the first few tens of thousand years after the moon forming impact. And then, of course, I asked the completely inappropriate question of what happens if we throw something into a lava lake. I'm going to chew up all my time showing this video. I already apologize, but it's too good not to. So let's have a look. This is Earth again. And this is a bunch of guys, none of which is me, sadly, who make videos of throwing things into a lava lake. So this is an active part of Earth. And what they've actually got, canister full of water. So jerry can full of water, they've thrown it in. There it is, plop, into the lava lake just down there. Now, first off, it melts all the plastic around it, and then the water gets released. And what happens when you water in a lava lake? It immediately vaporizes to steam. You get this massive amounts of steam bubbling up from there, from this jerry can that they threw in there. Now, this, believe it or not, this actually has scientific merit going somewhere with it. And then you can see, I mean, one, this dramatic effect, having this steam in this lava lake is amazing. But two, this is all forming this gas vapor and bubbling up out. It's adding to the atmosphere. And in fact, this is how a lot of the atmosphere and a lot of terrestrial planets anyway probably originally forms. It bubbles up from these magmatic systems. So, what sort of evidence do we have of this? Well, unfortunately on the Earth, we don't have anything left that's this old. It has a very dynamic surface, so a lot of the surface of the Earth has been destroyed, and there's no rocks from back there, but there are rocks that old from the moon. And in fact, when you look at the moon, an enormous amount of the surface of the moon is actually a relic of that magma ocean stage. So you can see when you look at the moon, so these black things, they're mare, they're basalts. That bit's a bit younger, so that forms when eruptions come up from underneath and fill in these older craters. But you can see this white stuff too, and most of the far side of the moon is made up of this white material. This is a mineral, it's a feldspar mineral. We call the entire rock seed an orthosite. And so this stuff is very light. So as you cool the magma down, it starts forming different minerals at different temperatures. So first you start forming some heavy minerals rich in iron and magnesium, and they sink straight to the bottom and form the mantle. And then a little bit after that, you start forming the lighter materials, the feldspars. And because they're more buoyant than the magma, they float up to the top. They form a scum on top of this magma ocean. And they sit there on top, and because they're light and nothing else happens to the moon, they stayed there. And so 80% of the lunar surface is a relic of this ancient magma ocean that the moon basically had initially before slowly cooling down and going senescent eventually. Now, the interesting thing about that, not so much for the moon, but for the Earth, is that the sequence of events that form the Earth-Moon system, this enormous impact, I told you it vaporized a lot of rock. Well, it certainly didn't do any favors to the early atmosphere. The actual impact, as far as we can date it, seemed to occur about 70 million years or so after the start of the solar system. So the Earth was quite a well-developed planet by that point. It had an early atmosphere. Most of that early atmosphere got blasted off during the impact. And we see fossil relics of this. So I don't want to get into too much detail of this, but xenon's a great example. It's a very heavy, dense gas. But a particular type of xenon, 129, comes from radioactive iodine. And the cool thing about it is that it starts off with nothing in the atmosphere, and then as the magma ocean degasses, it slowly builds up, and then eventually you stop forming this. So you can use it as like a watch, a stopwatch, to track how much atmosphere you've got through time and whether you lost any. Now, Earth is missing xenon 129. It has nowhere near as much as it should have. And what that means is that early atmosphere got blasted off when the moon-forming impact occurred. So that's quite peculiar, and it does mean Earth actually started with a lot less gas than it should. So what might have Earth looked like had it had all its atmosphere? We might be looking at it next door. So this is Venus. This is a picture of Mount Mons on the surface of Venus. It looks a little unusual compared to a lot of Earth mountains. The main reason is the surface of Venus is about 480 degrees Celsius around here. The rocks at that temperature start to flow like putty, so this is moving like toothpaste, and you're forming these kind of rounded peaks. Fairly unusual compared to Earth. This is a radar image that's actually draped over the topography, but the color scales are not that dissimilar to what you'd see on the surface. It's extraordinarily hot there. Now Venus, it's got a weird rotation. It's got a retrograde rotation, which is a consequence of how the planet was put together, but there's no real evidence for a big, late moon-forming impact. I mean, it doesn't have a moon, for a start, but there's no evidence of a big, giant impact like Earth experienced later on. And in fact, when you look at Venus's atmosphere, we have for a number of missions now, from the Russian Venera onwards, Venus seems to have retained a lot of its early atmosphere. So there's 129 xenon that's missing from Earth. It's there on Venus in a much higher concentration. So it seems to have preserved a lot of that early atmosphere. So this is peculiar, because when we look at other planetary systems, and there's a lot of exoplanets known now, we tend to think of them as being Earths, or we call them super-Earths, and we think of them as having liquid water in the habitable zone. But Venus is very much a twin of Earth, and it does raise the question of which one of these is more common in the universe. Are we going to see more Earth-type planets or more Venus-type planets? And a few of us in the planetary community are wondering whether it's going to be more Venus-like planets. And this has big implications. I mean, Earth is interesting. It has this system, plate tectonics, where the continents drift around. And that's cool for geology because it explains nearly all of modern geology anyway. But what it does for an atmosphere is it gives you a way of vacuuming CO2 out of the atmosphere. When you form a mountain belt or something, and it gets rained on, a lot of the CO2 in the atmosphere actually reacts with minerals in erosion and gets drawn out completely. So we have a sink. We have a way of sucking CO2 out of the atmosphere that's powered by the plate tectonic cycle. Venus doesn't have that plate tectonic cycle. There's nowhere for the CO2 in its atmosphere to go, so it just piles up, and you end up with this super thick atmosphere, 90 bars, 90 times Earth's atmospheric pressure at the surface of Venus. And it's an enormous greenhouse effect. It's a huge greenhouse planet. It's 480 degrees Celsius at the surface. It's hotter than Mercury's average temperature. So this is what happens when a greenhouse effect goes wrong. And of course, the big dichotomy for these two is Earth has life, partly because it's managed to regulate its atmosphere and its surface temperature. Venus, on the other hand, has none, as far as we know. And we argue about that. Maybe in the clouds there could potentially be. But let's just keep it simple. If we have a Venus-type planet, the chance of having life on it is very, very low compared to Earth. And this has fundamental implications as to what we're going to find out there in the rest of the galaxy. If Earth's quite rare and this moon-forming impact was quite rare, the chances of life might actually be a bit slimmer than we kind of optimistically like to believe. Right, so I'm going to move on post-lunar impact now, because it wasn't the only one that occurred by a long shot. So what happened to the Earth due to the other impacts post the big one? So after the moon-forming impact, we're into a period of Earth's history, which I love. It's called the Hadean, and there's no rocks left from that period, so everyone says whatever they like. But anyway, it was an interesting period of time, because the moon, actually at that time, would have formed just outside what's called the Roche limit, so about 1,800 kilometers from Earth, very, very close. So you're looking at, an enormous moon in the sky. The Earth was rotating about once every 4 hours, so the days were shorter. You would have this giant, big, molten magma ocean moon looming over you, at least in the early part. Lots of volcanism going on the surface of the Earth. So it was an extraordinarily interesting time. This is how Earth started off. Now, we don't have a record from this period, but we can get an idea of the impacting rates by looking at other bodies that got hit in the solar system. So we can look at the moon and look at how it got impacted. We can look at Mercury. We can look at the asteroids in the asteroid belt. And we built up models for how much asteroid impact should have hit the Earth. And this is an example of one such model made from one of my colleagues, Simone Marchi at Southwest Research Institute. And this shows each of these is an impact occurring on the surface of the Earth in 25-year bins as we start from the dawn of the Earth, going through the Hadean, which is where we are now. So each of these is a giant impact and the melt associated with it. And we're getting towards the end of the Hadean now. So after 500 million years now, you can see nearly the entire surface of the Earth has been smashed by these impacts. We go into the Archean and they continue on. And shortly after this, we have the earliest life appearing on the surface of the Earth, the earliest fossils. But for most of that early period, the Earth absolutely got hammered by these impacts. So what did that do? So that's the question I want to ask now is, what were these impacts actually doing to the Earth? There was a lot of volcanism, there was a lot of violence. These big ones, they are big enough. If they hit an ocean basin, they would evaporate everything. This is a sterilization event. Any life on the surface of the Earth would have been completely wiped out by vaporization of all the oceans. But what else did they do to the planet? Well, this touches a little bit on my side of things anyway. And what I'm going to show is a little controlled experiment. 2 models, and these are like slices through the Earth, if you like. This is the core in the middle, this is the surface here. And what you're looking at through here is mostly the Earth's mantle between the core and the surface. And this first example, I'll fast forward a little bit, it's a little bit dull. You can see the mantle flows kind of like a liquid. It's fairly solid, but over geological times, it actually convects away. Hot stuff rises up from the core, and gives you volcanism at the surface, so we get volcanoes on top of these little hot rising plumes, and the whole system's convecting around. But by and large, this is pretty boring. We're not seeing plate tectonics at the surface. We're not seeing any of that plate cycle that we associated with the Earth today. So it just sits there being volcanic, and that's about it. So on a planet like this, you'd expect the CO2 to eventually build up through time. You're not able to get rid of it if nothing else happens. Let's show you exactly the same simulation now, but now with that impact flux hitting it. So we'll see the effect of big impacts very quickly. If I press play, that was one. There's a 1,500 kilometre across impactor, and you can see the temperature field every now and again will go like it's got electrocuted. There are little impacts occurring. But as a result of these impacts, you can see in a lot of places, we're getting these little bits that's a little squirt of what we call basically plate tectonics. It's a cold plate at the top that's sinking down. It's dragging that CO2 back down into the mantle with it as it goes. So we have not quite plate tectonics like we'd call it today, but something similar. We have a way of actually moderating the atmosphere as a result of the tectonics going on here. And so we had a whole big paper on this, but the main take-home message from here is that giant impacts can actually change the complete way a planet evolves. We can go from being boring and just volcanic to actually having something like tectonics purely based on the impact history. And if we can have plate tectonics, then we have a way of sucking that CO2 out of the atmosphere and giving us something like the Earth as opposed to something like Venus. So shortly after this period of giant impacting, we have, as I mentioned, the very first fossils are observed. The first non-disputed ones are in the Pilbara. We have a bunch of stromatolites. These guys are in Shark Bay in Western Australia. And what they are on top of these, there's little blue-green algae colonies. They form these little bacterial mats, and they're photosynthesizing and producing oxygen and growing up towards the sun. But they form these weird dome-like structures called stromatolites. They get a little bit of sediment on them, and then the mat grows through that and forms the next layer. And they form these amazing little domes. And they can live in Shark Bay in Western Australia because it's really salty there. And the main predator for these things is marine snails, and they can't handle the salt, so you don't get them there. But we see these same stromatolites all the way back 3.5 billion years ago in the Pilbara in Western Australia as well. And so very, very shortly after those giant impacts finished, we had the conditions for life. And life seems to have got going very, very fast after it was able to, after the giant impacts end. So I would argue that a lot of the reason why it could was the atmosphere on the Earth, the conditions, the habitability of the surface of the Earth was primed. It was really set by those early impacting events from the giant moon impact through those Hadean impacts, which actually created an environment at the surface from which life could eventually get going. And I'm just going to leave you with a little Aldous Huxley quote down the bottom there, because let's face it, Our world at the moment, even as we experience it today, was not the same world that life evolved on when it first got kicked off 3 billion years ago plus. It was a very, very different and almost alien world. And it's always interesting to keep that in mind when we think about the conditions under which life has survived on the planet. All right, I'm going to leave it there. Thank you very much.
Great, thank you very much. In appreciation, please accept this.
Thank you, I sure will.
I just love all those images of early Earth. I'm sure there's some questions. Yes?
Yeah, so it's not so much that it had less impacts in total. I mean, then we're talking about the accretionary events. It probably had quite a number of impacts, but what it didn't have was that one big one at the end. So when you're talking about impacts, you have, small bodies. You have so many, it all just averages out. Then you kind of get the 100, 500 kilometre bodies, and there's differences between this planet and that. They're probably not important. And then when you get to the 1,000 kilometre plus bodies, this planet may have had 3, and this one only had 1. And that starts to get significantly different. And then when you get to the moon-forming impacts, they're so rare, particularly at that late stage, that it's almost a statistical anomaly. Earth got one just because it happened to be in the wrong place at the wrong time. Venus never did. So when you're talking about very low numbers of impacts at the really big scale, you'd expect not everybody had the same amount. Earth versus Venus versus Mercury. There's not too many 2,500 kilometre little planets floating around the early solar system at that time to smash into everything. So you'd expect there to be quite a difference, and for some reason Earth got hit by this particular one there, and Venus didn't, or didn't have the same style. So at the low level, there's no real statistical difference between the impacting, a little bit with velocity, but at the high level, when we look at the really big impacts, they're very much stochastic events, we call them. You might get more on one than on others, and that's just simply because you don't do a medical study and only pick 5 people and get a result on that. It's low number statistics. You could get any sort of result from that. And that's probably what happened with the big impacts on Earth.
Earth is pretty special. Warwick?
Now, given that Venus is closer to the Sun, if it had the moon creating event, what sort of temperature, if you played with an idea of what temperature it might moderate it down to?
Yeah, it's an interesting one because depending on where something like Theia came from, as it moves into the inner solar system, it picks up velocity, and so it would have hit Venus comparatively faster than it would have hit the Earth. So you're able to transmit a lot more energy for it, but so much of the specifics of these collisions are still yet to be worked out. We have models now where Robin Canup, for instance, prefers an almost 50-50 size the comparability between Theia and the Earth. She wants almost similar sized bodies impacting to give the Earth-Moon system. And some other groups, Sarah Stewart's group at Harvard, want a much bigger Earth spinning very fast and then a much smaller Theia hitting. And it turns out within what we know, all these end members are still permissible. We haven't quite worked out how to condense down the simulation realm and to say, okay, this one is allowed, this one is not. There's no real good observational constraints that exclude a lot of these models at this point. So all we're working with is the end product, which is Earth and Moon, look the same and their isotopes are similar, but there's a number of models that all give us that end product, and it's hard to actually condense down a little bit more than that. So when it comes to Venus, it's a similar situation where you open up the realm of possibility even more. And I don't think we're precise enough to really, if you got something hit Venus faster, you could have the same amount of energy delivered if you just had a bigger body hit it slower. So there's a bit of an ambiguity in terms of pinning down exactly what size it would be. And that's the challenge for us, is without any evidence of the impact itself, we're just looking at the aftermath. We're trying to reconstruct a sequence of events that fits, but it's not unique. There are a number of ways you could see these events through.
But surely if Venus is significantly closer to the Sun, then the heating effect of the Sun, given exactly the same circumstances that Earth inherited, right, for just for argument's sake, the heating effect would be greater nonetheless. I guess,
You're talking the atmosphere now, or even the impacts themselves?
well,
Yeah, it's tricky. I mean, the atmosphere on Venus may not have always been the same. In fact, we know it hasn't. We talked a little bit about...
I'm just talking about surface temperature, really.
Yeah, well, I mean, that's what I mean. The atmosphere predicates the surface temperature. The reason Venus's surface temperature is so high is because of the greenhouse effect of the CO2 atmosphere. If you took that atmosphere away, most of the heat would bounce off the space and it'd be a lot cooler on the surface. And so Mercury is actually cooler than the Venus surface on average, and that's mostly because it's got no atmosphere. So even though it's right next to the sun, a lot of that radiation bounces off again. It's only when you can trap that radiation with a greenhouse that it actually really starts to build up. And so the question then is, when did the greenhouse on Venus really kick off? And that's an active... I mean, that really needs going to Venus. I mean, it's actually a bit of a travesty. We haven't been there for the last 20 years, 30 years now. It is such a similar planet to the Earth. Earth could have ended up that way. We don't actually understand why Venus went that way and Earth went a different way. We don't fully. And yet we're going to other planets, we're pointing telescopes at other planets and picking out exoplanetary systems and calling them Earths, but we don't know what the reasons why Earth went one way and Venus went another actually were.
Well, if proximity is not an issue...
Oh, it is part. It's there for the atmosphere, but not the only issue.
But then conceivably, if you could, in the future, with greater technology, you could almost terraform, as they like to call it in science fiction circles, terraform Venus and produce a pretty habitable planet despite its greater proximity to the sun then.
Yeah. Well, if you sucked all the CO2 out of Venus, yeah. I mean, there's a story. If you took all of Earth's limestone, for instance, that's CO2, basically locked up as a rock, and you put it in a big vat of acid and release the CO2, you could put as much CO2 in Earth's atmosphere as Venus currently has if you took those rocks and just got the CO2 out of them and released it to the atmosphere. So you could make Earth uninhabitable and you could make Venus habitable if you could figure out how to strip the CO2 out.
Okay, we're going to have to move on, but it's all extremely interesting. Thank you, Craig.